The Transportation Research and Analysis Computing Center has been established in 2006 under a congressional grant under the Safety Lou Transportation Bill. The function of the center is to make computing capabilities widely used in energy research also available to the transportation research field. Users from across the United States can access TRAC supercomputers remotely while working with Argonne scientists to learn how to best utilize such systems. TRAC's researchers work on a variety of subjects of high interest to the U.S. Department of Transportation and the transportation research community in general, including areas such as fluid dynamics, aerodynamics, and hydrology, structural mechanics, occupant safety, and crashworthiness, as well as transportation system simulation, useful for congestion analysis, intelligent transportation systems, and evacuation modeling. The transportation simulation team at TRAC has been heavily engaged in the development of advanced simulation tools that can leverage these new technologies. The POLARIS development team at TRAC is led by Hubert Lai and consists of a multidisciplinary team of scientists at Argonne, including Joshua Auld, Michael Haupt, Vadim Sokolov, Bo Zhu, and Kuolin Zhang. The project is being managed by Brian Gardner of the Federal Highway Administration's Office of Planning. Jeremy Raw, also from the Office of Planning, serves as a technical advisor. There were a number of motivating factors behind the Polaris project, starting with the need for more advanced tools to support planning and investment decisions relating to intelligent transportation systems and other network operations. ITS infrastructure has the potential to impact a wide scope of traveler behaviors, including route choice, trip planning, driving style, and much more. In order to fully capture this diverse set of behavioral changes, a framework that unifies travel demand forecasting with network operations is ultimately needed. Furthermore, modeling how travelers interact with ITS systems will help to form a more accurate assessment of the benefits of current and future ITS investments. Polaris also allows for the representation of a wide range of these new ITS technologies and system management policies. These policies include information provision, managed lanes, incident detection, route pricing, and many more. The approach will also enable users to evaluate the key performance metrics related to mobility, reliability, and sustainability, given the variety of potential policy choices. This slide highlights some of the important features of the Polaris integrated activity-based network operations model. First, Polaris can create fully integrated agent-based demand, network, and operation models with a high degree of behavioral realism. The current model represents activity generation, activity planning, activity scheduling, trip routing, dynamic replanning, dynamic rerouting, and the actual process of traveling all as individual behaviors. The agents remain fully persistent throughout the entire simulation. Even the traffic flow is agent-based and is currently represented as a mesoscopic queuing model. The development of such detailed agent-based models is possible because of the highly efficient simulation engine developed in C++, which handles memory management, multi-threading, and execution scheduling throughout all of the software components. The code is also compatible with a wide range of operating systems and has been designed to utilize modern hardware architectures, including multi-core machines and cluster computing environments. These advances enable the execution of large-scale models within reasonable timeframes. The software has been demonstrated for the Chicago metropolitan region, which has about 10 million individual agents. The Polaris activity-based model can be used for general travel demand forecasting and is applicable across multiple scales, including regional, statewide, and national levels. The initial model was developed to evaluate the effectiveness of traffic management centers and other more basic ITS operations. Nevertheless, the model can potentially be employed for a variety of other applications. For example, it can be used to evaluate future ITS and other vehicle technologies, but also for quantifying pricing and lane management. It can be used for evacuation and special events planning, and for evaluating environmental and energy sustainability factors. The design of the system makes it particularly useful for large parametric variability studies. The Polaris Scenario Manager allows large numbers of case studies to be evaluated using high-performance cluster computers, such as the one available at TRAC. Several key performance metrics can be generated during a typical simulation run. Mobility measures, such as delay, accessibility, vehicle miles traveled. Sustainability indicators like energy use or emissions. And finally, reliability and resilience measures, which are useful across many different applications. The Polaris framework and Polaris activity-based model are being developed as part of an open-source software project. Developers can customize Polaris on different technical levels. The most fundamental components are the Polaris core libraries. These libraries provide tools for handling memory allocation, discrete event simulation, inter-process communication, and other low-level but essential features used across nearly all transportation system models. Problem-specific libraries implementing agents, objects, and functions to support specific simulation concepts are implemented on top of these core libraries. The problem-specific libraries are intended to be extensible and used across multiple projects. Accompanying these problem-specific libraries are other utilities that are not built on top of the Polaris core, but that are generally useful and necessary for model development. These include network editing tools, data conversion tools, scenario management, and more. Many of the libraries and utilities rely on mature open-source projects, such as SQLite, Spatialite, Boost, Python, and OpenGL, to handle details such as graphics processing, database management, and GIS functionality. Finally, full applications can be built from the general libraries to address highly specific issues. An example is the integrated ABM simulator. This is the simulator that has been introduced earlier in this presentation. The entire Polaris software framework, including the core libraries, object libraries, and simulation applications, is freely available for download, development, and usage from the GitHub repository shown here. The software is licensed under a permissive BSD open source license, which allows modification and commercialization provided proper attribution is given to Argonne. The code itself is being developed in C++ and is cross-platform compatible. The code repository includes scripts that utilize the CMake universal build system to allow compiling the code using the Visual Studio integrated development environment on Windows and the free GCC compiler on Linux. A few other less-known platforms are supported as well. This concludes the general overview presentation on Polaris. Thank you for your interest.